transmon circuit is not harmonic. Does anyone remember why we do not want a harmonic oscillator? So if you recall, in a harmonic oscillator, we have all the energy levels, right? Energy levels are n plus half h bar omega, right? So then energy difference between any two levels would be the same, half h bar omega. So you cannot really control where you are exciting the qubit to. So we intentionally go away from this half k delta square kind of potential to some potential that looks like cosine delta, right? And this delta is the relative phase difference between the two superconductors in the Josephson junction. That is the generalized coordinate. And we make it unharmonic enough, right? So the cosine looks something like that. And we make it unharmonic enough that we can just isolate the, 0 and 1 levels, right? And this energy difference, omega 0, 1, is different from omega 1, 2. So the answer is that the transmon circuit is not harmonic. And the reason it is not harmonic is we want to, yes, that's right. Saptagiri, not just for quantized steps, but even the harmonic oscillator is quantized, but the thing is that it is equally spaced. So please, note that the transmon circuit is made unharmonic so that we can change the energy spacing. Okay, this is the question that I really wanted to get to because we have been doing a lot of coding and we have been doing a lot of math, but through this course, I hope you will get to understand what is the difference between, doing the math on piece of paper and actually running the code on a simulator and running the code on a QPU, the actual quantum processing unit, right? So when we apply a gate to a qubit, for example, if I say create some quantum circuit QC, we have been doing things like QC H0 or QC.X0, whatever gates we are applying. What is actually happening, right? We are running this on a real quantum computer, right? That means we are running it on a real qubit. So we are not really simulating the output. If you're simulating the output, then that's a simulation. That's not the real hardware experiment. So when we are doing this on real hardware, we are not simulating it from ensembles. I intentionally put the word ensembles there. But yeah, so we are not simulating the output. It's something is being done on the hardware. You're not multiplying the qubit with the corresponding matrix. That is how we do mathematically, right? But so if I want to say, if I want to apply X gate, I could do like 0, 1, -1, 0, something like that, or 0, 1, 1, 0, something like that. But that is just on a piece of paper, right? So that's how I represent it mathematically, and I could do that. But how do we actually achieve that in the actual quantum computer? We discussed this, and I hope you recall, some of you, as you rightly answered, we are applying microwave resonator, different voltage pulses that can couple to this omega 0, 1 frequency, and that's how we actually make a gate. So please, those of you who did not answer correctly for either the second or third questions, please go back to the older lectures and make sure that you understand what's going on. Are there any questions? Okay, if not, then let's proceed to understand quantum noise, right? So again, just to recall, because we're talking about noise, we have to go back and look at what is actually happening in the hardware. And so we discussed this before, but I thought we'll quickly recap in a couple of slides, right? We have this h bar omega 0, 1 by 2 sigma z. We are sort of limiting the transmon to two levels, 0 and 1 levels. Therefore, we are expressing it as operator sigma z. The energy difference between those two levels is omega 0, 1. And so this is the Hamiltonian of just the transmon with two qubits, two states, and we have not applied any perturbation to it. Recall that we have something like, whatever our transmon, and then there is a microwave resonator, right? There's microwaves being applied, and then there is a readout from here, right? And so when we want to apply a gate, we do something with the microwaves. If you use a squid gate, right, that is, you have two Josephson junctions, right? You have two Josephson junctions, right? Then you can also apply magnetic flux, and you can control using the relative phase difference between the two junctions using magnetic flux or microwave. Either way, you apply this kind of the second term, the H bar omega d. This is the driving voltage or flux, and you have some sort of a pulse with some frequency and some phase, and like whatever gate you want to apply, based on that you apply this perturbation. So that depends upon how we are driving it, right? The oscillating term is what is inducing the transitions between 0 and 1, and that's how we are able to create the gates. Recall that we changed this entire Hamiltonian into a rotating frame. I'm not going to go through the math of that, but then after doing that, we simply got this, right, where we have sigma x and sigma y, right, in this, and sigma z is the actual two states, right? And then, so here we're writing it as sigma z, sigma x as Pauli matrices, but it is not the spin that we are working with. It is just that we're using the Pauli matrices to express that, right? So please bear in mind that we are not doing anything on spin. So this is what we call as the Rabi frequency. That is, you go from 0 to 1 and 1 to 0, and you keep oscillating between those. So you want to pick your driving frequency to be the energy difference between 0 and 1 states, right? And we have seen that if you have a time-independent Hamiltonian, that's why we moved to this rotating frame, so that we can make the Hamiltonian look like this. And then we could just do a unitary evolution on the qubit, right, using this unitary operator. And that's how we were able to realize different types of gates. So we are actually applying different types of microwave pulses or flux to do this qubit. And we also discussed how do we do the calibration and experimental control. The reason I am revising these is that to understand where the noise is generated from, we need to understand the real hardware. Because that noise is coming from, there is no noise in theory, right? In meaning that when I do math, I could just say 0 and 1, and there is no noise. And so our idea here is to understand the noise, where it is coming from, what are the physical sources of noise, and how do we model this noise. And for that, we need to first know that when we make the circuit, we don't a priori know what this Rabi frequency that we have in the Hamiltonian omega r is. And so what we could do is we apply microwave pulses. We discussed this also before. And then we see how it is going up and coming down. And then from that probability, we basically extract this Rabi frequency. And then we could also do this Ramsey experiment to talk about the dephasing time. This is one of the sources of error. That is, if I prepare the qubit if I'm making the transmon in a certain state, right? Let's say I apply some NOT gate, then let's say I excite it, then it's not going to stay in that excited state. It is going to, the relative phase difference is going to decay as time goes on, because it is not isolated from the environment. It is interacting with the environment around it. Although we are at millikelvin inside a cryogenic environment, still there is still some interaction with the environment, and that's causing this dephasing. And we'll try to model how this dephasing happens in a quantum channel. And we could do these again, apply microwave pulses with the delay time to measure actually what the dephasing time is, right? And so that's how we achieve these. And for example, if you want to apply an X gate, which is a NOT gate, then this is what we do, that we pick a particular constant frequency and apply the pulse for a certain duration. The reason we apply for a certain duration is that, for example, if I want NOT gate, then I want my u of t is given by e to the power minus I sigma rt2 by sigma x. right? Because X, sigma X here is giving you the NOT gate operator. And so we want this factor to be pi by 2, right? So then we can see that if I apply T is equal to pi by sigma R, then you rotate by 180 degrees, right? Pi, right? Then you get basically the X gate, and the pulse itself is shaped like a Gaussian shape, and so that you get this. So when we in the code, when we write something like QC dot X of 0, right? This is what it is doing. Then it transpiles. There is a command to transpile it. You should, when we are coding, you should understand what each line is sort of doing on the actual quantum computer, right? So then once you apply this QC.X0, then it is applying this kind of a some omega 0 e to the power minus t squared by sigma squared kind of a microwave pulse, which has some gigahertz frequency, and it is applying for a duration of pi of omega r, where you determine this omega r using the Rabi calibration in the previous step, right? And so perform a Rabi experiment to determine omega r, and then it adjusts the amplitude until a pi pulse swaps from 0 to 1. So that's exactly what it is doing when you apply QC.X0. Similarly, when we say something like QC.H0, we're applying Hadamard gate. So we're not really just multiplying with a matrix like this. This is just to do the math to show how this is. But this corresponds to a rotation along y by pi by 2, and then rotation along x by pi. So then we are applying two sequential microwave pulses onto the qubit, right? And so you have the first Gaussian pulse that's going to go along the x, and then the other one rotation around y, and that's how we can go from 0 to this state, or if you have 1, you go to this state. So we're not really multiplying with a matrix, or we are not simulating the output. Rather, we are applying these real microwave pulses to get that. And so our typical time scales that we need to note is the coherence time. That means if I prepare a qubit, so let's say I prepared a qubit in 0 state or whatever we say, we initiated a qubit, and I just left it alone. There is some question here. Does applying it for a certain time mean multiple pulses of the same frequency? So it's actually a wave packet, Satvik. That's why we are showing this as a Gaussian. Right, so you can make the Gaussian only with like a wave packet. So you have 5 to 6 gigahertz, and so you're applying like a Gaussian pulse. So the time t, we are applying the Gaussian pulse width for that time. So yes, in some gates it is applying different pulses. For example, when you want to do the Rabi oscillations, you apply different pulses. So I hope that answers your question. So it depends upon the gate whether you apply multiple pulses or singular pulses. Okay. Any other questions? So the coherence time is tens of microseconds. So that is, if you prepare a qubit and you don't do anything to it, you don't measure it, you don't do anything, you just leave it alone, then over the time it's going to change. It's going to interact with noise, and it is going to change. It's going to interact with the environment, and there's going to be noise creeping in, and it's going to change. But if you immediately measure it, then it should be fine, right? So far, what we have been doing is we've been making immediate measurements. We have not really done any prolonged measurements. So a typical single qubit pulse takes around 10 to 50 nanoseconds, right? And the coherence time is tens of microseconds. So then, you are pretty good with respect to a few gates, right? So like, let's say 1,000 gates, right? If I apply 1,000 gates, then maybe 10 microseconds. So as you keep applying more and more gates, then, you're going to see the effects of decoherence. That is the interaction with the environment itself. Then we have also seen this coupling strength. That is, if I want to couple two qubits or multiple qubits, then recall that we have Josephson a junction, a capacitor, right? So you have a Josephson junction, and then you have a gate capacitor, and then you have the gate voltage, and then we can have a shunt capacitance if you want, right? And this is the gate capacitance. This is how our superconducting transmon circuit looks like, right? But this generates one qubit, right? Single qubit. But if I want one more qubit, I make another uh, copy like this. So instead of Josephson junction, you could also have a squid if you want. But if you have a squid, then basically you can control it with a flux line. But whatever it is, one qubit is one of these circuits. If I have two qubits, then I join them using another resonator so that they can be coupled into a two qubit system. And that coupling strength is typically of the value 20 to 50 megahertz, right? Again, that means that you have, again, the actual microwave pulses we apply are in gigahertz range. And so you have a lot of time before it decoheres, right? Um, so that is the experimental part. And so today we are going to look more details into how we can estimate these errors, how we can model these errors. Before we proceed, are there any other questions on what we discussed so far? Okay. Can we somehow print this data in code that for a particular code, which pulse is applied and for how much duration? Yes, I think so. I have to look up the exact thing, but I think you could print it. Yes, for a particular gate. Yes. So I guess what you're saying is like if I'm applying QC.X0, you want to actually ask the computer to, after it transpires, like what it's exactly doing. I think there is a way to get those, but I do not exactly know how to get those, but there must be a way because it has to apply those. So that's a good question, Subhanshu. Um, any other questions? Okay. So then let's talk about gate errors and infidelity, right? So there are different types of errors like we just discussing. So in general, fidelity means that you faithfully produce the state you want to produce. Anything that moves away from that state is, you consider it as an error, right? So there are different types of error. The simplest type of error is leakage, meaning that when we talked about this enharmonic oscillator, we said that we made it enharmonic, so the energy spacing between different levels is changed. But we have, as I'm drawing here, we have 0, 1, and 2 levels, right? So when we consider the Hamiltonian as sigma z, that's again an approximation that assuming that the 0, 1 are that omega 0, 1 is significantly different, or omega 1, 2 is much higher than omega 0, 1. That is, when we apply a pulse with omega 0, 1, we assume that you are not going to leak into 2. We're only going to between 0 and 1, right? So if we do leak into 2, right, or higher transmon levels during fast pulses, the reason why you would leak into 2 is, remember that we are applying Gaussian pulses or wave packets. And when you make a wave packet, like even if you apply like a rectangular pulse, it is not a single frequency really, you have multiple frequencies, right? And so those multiple frequencies, there will be some frequency that would give rise to this omega 1, 2, where you can jump to leak to the second state. So that is one source of error. The other two sources of error, one is the incoherent error, which comes from talking with the environment. Although again, we're at millikelvin, there is energy relaxation, there is dephasing, and there is residual thermal population. That is, you excite to 0 to 1, but some are left in 0, some are left in 1. And there is coherent errors as well. That is the way we apply the pulses. Those pulses themselves can have distortions. There could be crosstalk between different qubits when we couple them with the bus resonator, right? There could be frequency detuning. And most importantly, we cannot, the way we know that there is an error is only when we measure, right? So the error is, so we have this, we have our circuit, this is the actual qubit, right? And we apply a microwave pulse to do the gate, and then we read it out. Until I read out, I do not know whether there is an error or not. And when we do theory, we often consider that the readout mechanism is ideal. That is, the ideal readout mechanism is it doesn't change anything. It doesn't itself give rise to error. It faithfully measures what is there and doesn't do anything else, right? But that's not true. Any device is going to somehow get entangled with your whatever it is reading, because entanglement, recall, we discussed, is correlations. So when I read something out, that means I want my reading to be correlated with what I'm measuring, right? That's what a reading is. A reading, a measurement is a correlation, right? Otherwise, it's meaningless. If I cannot say that if there is 1, I should see the meter click 1. If there is 0, it should go to 0, right? So whatever reading that I see on my meter must be correlated with the actual thing, right? So the device actually gets entangled, and that itself could lead to a certain error. So we cannot really decouple the state preparation from the measurement itself. Are you able to follow me? We cannot say this is the state preparation error and this is the measurement error. We cannot really do that. In some sense, probably we can measure the relaxation time and we could say something, but still, even when we're measuring the relaxation time, you bring in the measurement device somehow. You cannot remove the measurement device, right? The way I try to explain often is, imagine you have a lake, right? There are waves in this lake, and you want to measure what is the intensity of these waves or what is the frequency of these waves. So you have to stick something into that water to measure that. So, but when you stick it in, then you're going to disturb the water. And so you're going to slightly change the frequency or slightly change the amplitude. If you stick more meters in at different places, you're going to change it more, right? So we cannot really decouple our measurement from the gate error or the preparation error itself. Any questions? So somehow we want to quantify this noise, right? So we can see what is happening, right? So for example, like we saw yesterday that when we prepared these Bell states, right, we did find that sometimes, so we tried to prepare, like, let's say, this kind of a state where we had 0, 0, plus 1, 1, and then we saw that the simulator would just make it 0, 0, 1, 1. That's it. You don't see in the simulator, you don't see any 0, 1 or 1, 0 states, right? But when we did that with the real QPU, then we saw that there were some states that look like 0, 1 and 1, 0, right? So now that is not the only error that we it need not be that we prepared 0, 1, 1, 0 in the state preparation. So sometimes you may have prepared, like, let's say 0, 1 state, but due to a read error, due to a readout error, it read it like 0, 0. You see what I'm saying? That there could be two types of errors. That is, you actually made a wrong 0, 1, 1, 0, but then the measurement itself could misread and misassign 0, 1 to 0, 0, or misread 1, 0 as 1, 1, right? So even the outcomes that you would think are actually correct could have come from a double negation, right? You prepared a wrong state and read it wrongly, and so you ended up with the right measurement somehow, right? So so some correct measurements may result from incorrect states, right? So we may need to somehow describe this partial correctness or mixedness of the states, right? So the question we are asking now is, how do we represent noise or imperfectly prepared quantum states, right? So we have mainly focused our discussion on transform superconducting based quantum computers, but those are not the only type of computers. There are, photon, you can make qubits with photons, you can make using ion trap. And so all these preparation methods would have different types of errors. But what we are looking for is some sort of a general framework to represent noisy or imperfectly prepared quantum states, right? So that's why we introduced density matrix, right? We saw that not all states can be represented as these combinations of state vectors, right? The state vectors, like when we represent in like state vector like psi, or like I could say some 1 over square root 2 psi plus some 1 over square root 2 phi, something like that. I could represent, I cannot represent real qubits all in states like this. And so that's why we came up with density matrices. I hope you recall our discussion on density matrices. So density matrices, we can use density matrices to make convex combinations. And the idea with this convex combinations is that I could make something like K, PK, rho K. That is, I have sigma K, PK, the probabilities all sum up to 1. These are not probability amplitudes. These are probabilities themselves. That is, you do not need to square them, right? This is probability itself, right? Whereas here, this is probability amplitude, right? So if you were to sum these coefficients do not sum to 1. So it's not a convex combination. But with the density matrix, you can make a convex combination. So you can really express states that cannot be expressed as a sum of the state vectors like that in a convex combination of density matrices. So density matrices, when we were discussing that, I promise that we will come back to this when we are studying decoherence and noise to see why this is relevant. And that's exactly where we are now. So we are going to use density matrices somehow to represent, to capture the quantum coherence through off-diagonal elements, if you recall, how we get those off-diagonal elements, right? So if you don't recall, simply if I have something like 0 state, right, I can represent this as 1, 0. So the density matrix for this would be 0 ket and 0 bra. So that would be 1, 0, 0, 1, right? And so then you can multiply that, right? So that would be sorry, so that would be 1, 0, and then you do 0 and 1, right? No, and so there should be 1 over square root 2 and 1 over square root 2, and so you have the proper normalization, and the trace of rho is always 1 to normalize the probability. We already discussed these in density matrices. So if you do not recall that, go back and please revise that. That would be important for understanding noise and decoherence. But we are going to limit to only single qubits because of two things. One, it is not easy to do with multiple qubits, and I'm also running out of my quantum computation time on the real quantum computer to simulate these, right? So rho allows us to quantify noise, decoherence, and fidelity. So if we prepare, in general, if we prepare a single qubit, right, I can express the density matrix for a single qubit as a 2 by 2 matrix, which has P0, P1, right, and some C and C star, right? The C and C star off diagonal elements, they are simply like 0, rho 1, right? And C star would be 1, rho 0, opposite of that, right? The conjugate. And P0 would be 0, rho 0, right? And then you would have P1 to be similar, right? So or you could take P1 to be 1 minus P0 because the trace of rho must always add up to 1. So there is also a physical matrices constraint, that is the off-diagonal elements are always less than or equal to P0, P1. We're not going to go into more details on why this is, but it is very straightforward if you want to look it up. And whenever we are applying matrices, whenever we are looking at these matrices, you remember that they're in some computational basis, right? So here we're picking this basis, right? So now what we want to do is we want to quantify the error. So, or we want to come up with something. So we want to consider quantum circuits that produce some output density matrix, right? Rather than describing them as states. Again, the reason we are doing this is real states are better represented by density matrix rather than the Ket notation, right? Because real quantum mechanics is not done in Hilbert spaces, but it is done in a lab, right? So that is why we're using this density matrix. So what we want to see is this output density matrix rho. We want to see how close it is to rho 0, right? In case of a single qubit, we can just sort of compare, we have only 4 numbers, and so we can sort of compare these 4 numbers and see how close we are. But what we are seeking is no matter the dimensionality, we want a single number that can quantify the closeness between rho and rho 0, right? So we want to find a scalar measure, right? So here, note the word scalar. Can anyone define what a scalar is? Are you with me? Yeah, that's good. What's a scalar? Any number, magnitude. Integer without a face, okay? Tensor of rank 0. Which does not transform under any transformation, be it translation. Very good, Anuradha. You're very close. So it is a scalar is it doesn't transform, meaning it stays the same. For example, if I look at, let's say, I look at a vector A, right? I write it as 2i plus 3j or whatever in some ij coordinate system. Abhilash, I think it shows up when you write on the screen. It shows up for everyone. So I can express some vector A, let's say as 2i plus 3j, right? So would these 2 and 3 be scalars? Would the components of a vector be scalars? Anyone? Did you follow my question? Okay. Let's see, 3 new messages. No. So that's right. So they won't be scalars, although they look like numbers. The reason is, if I were to change my basis instead of ij, right, this vector is actually a physical vector. So let's say I have I and j, right? So let's say 1, 2, 1, 2, 3, whatever. So this is actually a physical vector. Independent of the coordinate system, this is how that looks like. That is the actual vector. Now, if I were to rotate the coordinate system to something like I prime and j prime, then in that coordinate system, the vector would not be 2i plus 3j. It would be something else. That is, the components would change if I rotate the coordinate system. So then the components are not really scalars, although they look like numbers. So here I am saying find a scalar measure I'm not saying find one number. I'm saying scalar measure. And that scalar measure has to do with the trace. And trace is basis independent. No matter which basis you look at in, the trace is always going to be the same because the trace is the sum of eigenvalues of that. We have seen that when we're discussing the trace. So we want to find a scalar measure, meaning we want to find irrespective of any basis, because when we write the density matrix, we write the density matrix in some basis, right? So I don't want my whatever measure that whatever measure I would come up with, I don't want that measure to change just because I change the basis. No matter which basis I use, right? I want whatever measure that quantifies this noisy state must be the same irrespective of the basis. That's why I'm calling it the scalar measure. I hope you're able to appreciate that the word scalar is misused so many times. So sorry that we had to take a detour to express it, and also take a little while to enjoy the beauty of how trace is a scalar. It's really beautiful. If you understand linear algebra, should be just jumping out of your chair with joy. Um, uh, Coming back to the fidelity, so we are using trace here because we want a scalar measure that's independent of base. I'm not going to go into the derivation here, but this is inspired by classical fidelity definition. So rho 0 would be the ideal state density. Rho is what we're preparing, right? And this trace would always maximum, it's a real number that varies between 0 and 1. So if your trace, if your fidelity is 1, that means that you have faithfully reproduced the original state. If your fidelity is 0, that means the state you produce is completely orthogonal to whatever you had. So as we are talking about states, I understand that it is somewhat hard to switch away from 0, 1 kind of states, but we have to ultimately come to density matrix, because in an ensemble it doesn't make sense to say single particle is produced in 0 state, because this 0 state is not for a single particle. It's an ensemble. And so it makes more sense to represent with rho. And then you can swap this. It's a simple. Yes, Satvik, please go ahead.
Sir, I wanted to confirm. Did you say the a scalar is basis independent? Because
Yes.
I'm referring to Ballantyne's first few pages where it's when you have an inner product of a vector space element with its dual space element, that is with its functional, so you get a scalar, right?
Okay.
And that would be a definite scalar, and it won't be some just arbitrary scalar.
Okay.
Does that not make it dependent, or does that not make it related in some sense?
The inner product won't change when you change the basis. It
uh,
would still be the same. For example, if I take this vector A, right? If I do A dot A, that is not going to change if I rotate the coordinate system, A dot A is still going to come out the same.
okay, sir.
A might look different, but A dot A is going to come out to be the same. That's my understanding, that the inner product, but I mean, it shouldn't change with the basis.
Okay, sir.
Okay.
Thanks.
Okay. Any other questions? Okay. So the fidelity is also. Was there a question, Satvik?
No, sir.
Okay. So you can confirm for yourself that this fidelity is symmetric on the, because it is measuring the overlap between rho and rho 0. So it is like, you walk from point A to point B or point B to point A, it doesn't matter where you start and where you go. You're measuring the distance between those two things, right? So let's say now, again, let's go back to the pure target state. Let's say we want to prepare our system preparation the way we are making the qubit. Our rho 0 is in some state given by psi 0, right? Then my actual state comes out in rho, then I can measure the general fidelity using as the expectation value of the rho, right? Of the actual rho is the output density matrix, right? So F is the probability that the noisy state rho would yield the outcome psi zero when you make a projective measurement, right? So if there is no noise, and rho is equal to rho zero, then rho would also be psi zero, right? Then if I look at F of rho zero, right, that would be psi zero, rho, psi zero, which would just give you one, psi zero, psi zero, psi zero, psi zero, right? So that would give you one. So that means you have noise-free case, right? With noise, then we cannot really say anything about this as psi zero. So it would be whatever it is, and the overall F fidelity would be less than one, right? So this is again, if we are expecting the output state to be something like a pure state psi zero, right? If we expect the output state itself to be, that cannot be expressed like this in a pure state, then we have to go back to the definition here, right? So we are going to work with these kind of pure states and see how what is the fidelity of things that we are going to do. So I'm going to cut, copy, paste the link to the Colab document to now actually do the runs in the chat box. So again, please make a copy for yourself. And I hope you're able to now see the code. Yeah. So please make a copy for yourself, and we will go through. I'm just going to run these so that it'll get connected and run. And so come back. So what we're going to do is we're going to just initiate one single transform qubit in zero state. And we're going to do n times. That is, we're going to do n shots, right? And we'll measure the probabilities, which will vary based on n. I just put some number here, whatever I got with whatever shots. So you don't have to get this, right? So it will vary based on n. So if you get things like this would be your P0, this would be your P1. Remember what P0 and P1 are. This is the P0, which is nothing but this. And this is what we have. Let me change the color. So this is what we defined as P0. So that is what is nothing but fidelity for a pure state if we are trying to produce zero state, right? So then that would be like 0.9966 in this case, right? I'm not saying that is the actual result. I'm just saying putting just some result. That means that, this is pretty good. This is very good that it has high measured fidelity, right? Or nearly ideal state preparation, right? You're preparing what you want to prepare, right? So let's go back to the code. I hope all of you are able to run the first two cells. Please change your token and API key. Do not use my key because I do not have much time left and I would like to run these. How do I? It's somehow stuck. Yeah, I tried to escape. Just give me a second. Okay. Sorry about that. So can you please confirm that you're able to, you change your API token, you change your instance, right? please confirm that you are able to access the code and change those. Okay. I have one reply. Okay, great. 2. Okay, 3. So because we are doing this over Zoom, sorry that I have to ask you to answer so that I know that you are able to interact and you're actually following. Otherwise, it would be waste of your time and my time, both. Okay. Okay, that's great. So I hope others are able to run this. Let's see who has not replied. Subhanshu, uh, Priyanshu, Rohit, Priyanka, Nityansh, Murari, Ipsa. Okay. Anuradha, that's fine. That's okay. Bit slow, it is running. Okay, that's okay. As long as you're able to access it and run it. Abhilash, I hope you guys are able to run it. So please change your API token in the instance. Don't forget to do that. So I'm just defining one function here. Um, um, that is run circuit, just a common function because I don't want to write this backend every time. Remember, when we say backend, it is one of the actual QPUs that we are picking. And so we're picking the least busy one, which would either be IBM Brisbane or IBM Torino, usually. For it depends upon your geography. And also your plan. I think for free plan they assign those two. Um, so and then we are just running the sampler, and then whatever result we are getting, we are transpiling the qubit. Where we are so the instruction. So I think Subhanshu, you asked a question before about getting the actual parameters. So that should be in this ISA. So this is ISA, I think instruction system or set architecture or something like that. But that ISA should have your actual voltage pulses and durations, which you should be able to access. I'm not sure. But then, this is just a function to run everything. So, let's compile it. So let's try for single qubit fidelity. I just put 100,000 shots. Maybe I should just put less shots in order to conserve my number of shots or the runtime. So, that will work. That's comma. So you can also, you can just make 10,000 to it. It doesn't matter. So then what we are doing is we're just initiating quantum circuit with one qubit, right? And then we're going to pass that off to our run circuit, which we already made the definition. And then for this, it is going to calculate the probabilities, right, of it being in, it is going to calculate the diagonal matrix elements. That is what we are trying to calculate, right? So remember that the fidelity is, we're calculating these diagonal elements, right? P0 and P1, right, that I'm writing in green here. That is 0, row 0, and 1, row 1, right? And our fidelity is given by this 0, row 0, right? So you can check that because I am just initiating it into 0 state. So I want my row 0 is just 0. That is, I want that row 0 matrix to be equal to 0, 0, right? So then my fidelity is 0, row whatever is the actual one that I get times 0, right? Okay. I think somehow this is slow. Um, so let's see. Maybe it is because all of us are running at the same time. Um, so let's come back to that. Hopefully it will run. So, but it shouldn't take more than 1 minute on the quantum computer. It is just basically it is putting it in the queue. So we'll come back to that. So you will see whatever is the fidelity, experimental fidelity, that's how you can measure it. I hope and you can change the number of times and check out for yourself whether that changes or not. So this is, we did not apply anything. We just prepared the state. We just initialized quantum circuit one. That means we already initialized it in zero state and we did nothing else, right? Now, what we want to see is we want to see gate fidelity, right? So for gate fidelity, I'm making it in state zero. This QC, when I say it is making it in state zero, right? And then I am applying X gate, which is going to make it a NOT, right? X gate is a NOT gate. So that's what I prepare it in zero, apply X. So I get one, and then I make a measurement, right? And then I'm going to print again these measurements. So the state I want to prepare then in that case for the X gate, so for the X gate, the state I want to prepare is my rho zero is going to be 1, 1. Right? So then my fidelity for X gate would be 1 rho, whatever I get, 1. Right? So that would be, P1, right? That you can see here. So I guess there is some issue with the way it is running. So I hope we can come back to that and see what is happening maybe later. But let's go back to the slides and see how to do the X gate. What way was the, yeah. Okay. So now when we add more gates, like for example, I initiated 0. This is not 100% fidelity. I'm not getting 100% fidelity. But when we say we are not getting 100% fidelity, it is okay. You got the results. That's great. We'll come back to the results, Anuradha, in a minute. So when we say we are not getting 100% fidelity, you have to be very careful here. That is, you cannot tell when we say we prepare a state 0. That is an ensemble. You cannot tell the difference between the ensemble and the measurement error or decoherence, because ultimately we have to measure it to see whatever is coming out. That this rho is whatever. I have to make so many shots, right? For which I have all these instructions and I'm doing that. So I cannot really tell what is happening, whether it is state preparation or whether it is measurement. I cannot separate them. So if we have longer circuits, there are some questions. Okay. Okay, I think people are getting results and they're pasting them. So I guess we did get the results. So you see that it is 87%. It is able to reproduce the actual state. So 12%. So here, when I say 87% of the time it is producing 0, 12% of the time it is producing 1, then what I cannot say is whether this 12% is error, whether this 12% is noise, or whether that 12% is actually the characteristic of a real ensemble. Because when you simulate the quantum computer, there you are assuming that each particle can be initiated into a 0 state with certainty. There is no probability there, right? But that is not the state preparation. State preparation means identically prepared system. Recall the definition of state preparation, right? Identically prepared systems, right? So, Mahesh, did you have a question? Okay, the characteristic. Okay, I guess you're just pasting the answers. So we cannot tell whether this 12% is error or whether that 12% is actually part of the ensemble. That's how the real thing is, right? So when we have gates, as we add more gates, you may get more control errors. You may get more decoherence. That is because, for example, let's say I initialize the state in 0. I apply a NOT gate, which is X gate, right? Then I have 1, right? And then I make a measurement, like how we just did, right? In the NOT gate, right? So then that is this second code that we have here. I'm going to just run it. So it is going to take some time. Then the error that you get for 0 state and 1 state may not be the same, because 1 state is a higher excited state, and so it decays into the 0 state, and 0 state itself is the ground state, which is more stable, right? So there is relaxation to 0 state, but there is no such relaxation when you are initializing the state itself to 0. In case of 0, it is decoherence, meaning that it is interacting with the environment and you could have excitation or something. But in case of 1, it can decay, right? So measurements on states like 1 are typically more noisy and biased, right? Even without gate noise, if you just keep measuring 1, you will see that the fidelity decreases over time. That is, I generate the NOT gate and I measure this at different time points. Then you will see that there is some relaxation. So there are two components. That is the state itself, the way we prepare the state, and the gate-induced noise. And we cannot really tell what is what. We cannot really completely decouple. We could measure the decay time or something like that, but still we cannot tell in whatever percent we get. I think we got the results here for the NOT gate. And so we cannot tell whether this 14% is due to the gate itself or it is due to the difference in the state. Are you following me? Are you with me? Any questions? Okay, Mahesh, know for you're following me or you have no questions. I hope no questions. Okay. Anyone else? Do you have any questions? Okay, if not, let's proceed, because it's not so easy to calculate the fidelity if you have, let's say, square root of x gate, right? X gate is like you use the Pauli matrix 0, 1, 1, 0. So square root of x is, you take that half times this. So it is like a rotation around x by pi by 2, and you have this extra phase, right? So it's a block rotation around x-axis. So now let's say I prepare a state in 0 and I apply SX gate, right? Then I am not going to get, in the previous two examples, we got either 0 or 1. So it was easy to check what the fidelity was. But here, when I apply SX on 0, I am going to get, something like this, 1 plus I and 1 minus I. So I'm going to get a phase, right? And I get state 0 and state 1. Right, so then I have to consider P0 and P1 both for getting the fidelity, right? So we have to sort of kind of look at what the fidelity is. We have to look at even the off diagonal elements, because now you have 1 plus I and 1 minus I. We have to recall that for the row 0, we had P0, P1, C, C star. So previously, I looked at P0 when I created state 0. When I applied the NOT gate, it sufficed to look at P1. But when I'm applying SX gate, I generate not 1, 0 or 0, 1, but I generate something that has both entries, 1 plus I and 1 minus I. So I'm creating a superposition of 0 and 1. Even like a Hadamard gate, you would do that. But here you also have a phase, right? And so you basically get, you have to account for the C elements as well, right? So you can find fidelity on a real SX gate, which is psi 0 is SX times 0. That is this state that you see here, 1 plus I and 1 minus I. So you can show that fidelity should come out to be half of P0, P1 plus imaginary of C up to some global phase, right? If I just consider it as this state up to some global phase, then I can write this as P0 plus P1 by 2 and imaginary part of C. But P0 plus P1 is the trace of the density matrix. So that must be 1. So I don't even need to compute that. So that just becomes half. And so all I need to do is I need to calculate what this coherence phase is, right? Which is not very straightforward, because what we get are the probabilities. Whatever we're running on the code, if I go back to the code, what I'm getting is P0 and P1, even before P0 and P1. Now we need to get the off-diagonal elements of the density matrix. So what we need to do is remember that any 2 by 2 matrix, I can write any 2 by 2 matrix, I can expand it in terms of polymatrices. So I can write any 2 by 2 matrix. For example, if I have some 2 by 2 matrix rho, then I can write that as 1 over 2, the identity matrix, plus expectation value of sigma x, expectation value of sigma y, plus expectation value of sigma z, right? I can express it like this. That's what is written as half I plus r dot sigma here that you see. So what I need to do to get this imaginary c is I need to calculate the expectation value of sigma y, right? So I need to get for the gate where Sx of 0 is minus y. So I want to get this imaginary c as, so sigma y is minus 2 times imaginary of c. So if I want to get the fidelity, I need the c. So I need to calculate basically the expectation value of sigma y, right? So what we do is we create the state, but then we rotate our measuring basis. Our measuring basis is always in z if you, unless you change it, right? So we rotate it, we rotate the basis, right? That is, we apply a Hadamard gate to rotate the basis, and then we measure the sigma y, and then that's how we compute the fidelity, right? So that's what is in the code, right? The important point to understand here is that unlike the previous two things, here I am needing an off-diagonal element, right? So this, whatever, when I print the results, it's not going to give me off-diagonal elements. So I actually have to measure the off-diagonal elements by rotating and measuring sigma y, and then from there you can get the answers. So okay, let me not run this, but you can see here that when you apply square root of x gate, you will see that I used 100,000 shots, and I get the fidelity to be 0.46, right? So it's not very good, right? But again, we cannot tell the difference between state-dependent relaxation and the gate-induced noise. And sometimes to measure the fidelity, it is not just a direct measurement. The measuring the fidelity itself would require extra rotation, right? Like in this case, for measuring sigma y, I need to rotate. That itself can induce error, right? I hope you're able to follow me. So that itself can induce error. So we cannot tell these apart, right? But nonetheless, we expect that those errors may be bounded. They would have a lower bound somehow. And then so, it would be within that, last two digits or whatever. So still we could say something useful that half the time, you're preparing this. But again, this kind of fidelity assumes Copenhagen interpretation, meaning that it assumes that each single particle can be assigned a state, right? So then the next gate is echoed cross-reference. So here, instead of having diagonal this way, you have the diagonal the other way. So it can be represented as X gate, but with a direct product of I, right? So and the diagonal matrix. So you get this. So what this echoed gate does is it cancels the unwanted qubit terms. So you can apply that on any of these states, like 0, 0 or 0, 1 states, right? And you can see what result you would get if you applied on this, right? So for example, this element is non-zero, which means that you have 0, 0, whatever UECR, right? 1, 1, 1 is I by root 2, something like that. Right? That's what it does, right? So in other words, when you apply U on 1, 1, then you get I by square root 2 0, 0 plus I by square root 2 0, 0, something like that, right? So that's what it is doing. So again, when you want to measure the fidelity, if I want to prepare some state phi plus after applying this, right? In the noise-free case, I'm supposed to get these. Again, that is from the matrix that we have. And so for that, I have to prepare this state. This is the phi plus state that I want to prepare, which is 1 over square root 2, 0, 1 plus 1, 1. And so that is what I'm using to get the expectation value of the fidelity. But this is not the basis that I measure in. So I have to rotate the basis again, right? I have to rotate the basis to make a measurement on that. So I have the ECR gate here, and so I have to perform a rotation to measure this, and so that itself could induce some error, right? So let's see. I ran this, and you can run it later for yourself. And we see that that comes out to have a fidelity of very low fidelity, that is 0.22. Again, I will stress that this fidelity is defined by assuming that you have a state vector for each single particle, which may be meaningless if we consider the ensemble representation. So some people may call it noise, but some people may call it, well, you cannot really tell ensemble from the noise. That is, it is not just due to gate, it is also dependent on the state preparation itself. And your ensemble itself, it may not be an error. That's what state means, that you create this probability distributions. And the last thing that I want to do before we proceed further is something, a time delay experiment. So let's see, let me run it to begin with. And so I can, it can be computing. Okay, so here I'm going to click run, and then we'll see what that means. So what we're going to do is we're going to do two things to measure decoherence. That is, we talked about the state relaxing, right? So I can initialize, I can make my state preparation to have 0 or 1, right? And we saw that 1 can relax back into 0 state, right? So we have this decoherence. So what I'm going to do is I initialize first into 0 state, right? So first type of measurement is what I'm going to call as a series measurement. So I'm going to initialize into 0 state, right? And then I'm going to measure it after T0, right? So then I have my next state. For the next measurement, my state preparation is M0. Then I'm going to wait for some time delay T1 and then measure, the another time, first time, right? So I'm going to get some result here, right? I'm going to get some result here. And every time I get some result when I measure, so I get result 0, right? A result 1. And then the next time my state preparation is going to be M1, M0, 0, and then I wait for some other time T2 and measure again. That gives me the third result. Are you following me? This is a series measurement. That is, I created the state and I'm measuring the same thing. So when I say I created the state, this is not a single shot measurement. This is, I'm creating 100,000 times or 4,000 times, how many ever shots I have here. I'm making it those many times. And so when I say 0, T0, M0, I mean to say that I created 0 state 4,000 times and waited for T0 and measured 4,000 times. And those 4,000, again, I'm waiting for T1 and measuring again, right? But it is the same 4,000, right? Whatever I created in the first time, 4,000, I'm just following up at later times. I hope you followed that. Do the same thing with state 1. That is the series measurement. So create, wait for time 0, make a measurement. Next time the state preparation is 0, 1, wait for time T1, right? So on and so forth, right? So if I pick this one, T2, so T2 would involve, T2 would be like when I'm making a measurement at T2, measurement M2 would have waited for a time of T2 plus T1 plus T0. That is the total time that I would have waited for making the second measurement, M2, right? So that is the series measurement that I can make on 0 and 1. And then I'm getting the result, which is the probability. And I can plot that probability of 0 or probability of 1 as a function of time, right? But then I can also do a parallel measurement, meaning I make 0, again, make it 4,000 times, wait for t0 time, make one measurement, get the result. Now make a fresh 0. Now wait for t0 plus t1 and make a measurement, right? Then again, make 0 4,000 times, right? Wait for t0 plus t1 plus t2, right? And measure it again. So in the parallel measurement, I'm always just making it from the state preparation and then waiting for different times and then measuring. But in case of series measurement, I'm making the measurements on the same ones that were produced first. So my state preparation itself is different. In series measurement, for example, if you look at T1, my state preparation is M0 times 0. Whereas in parallel measurement, my state preparation is always the same. Right? Did you follow that? Any questions? So let's look at what result we got here. So so when you do the same qubit in serial measurement, you see that the probability is dropping as you go for longer and longer, right? This one more or less stays on average better than series measurements, the parallel measurements, and obviously this is 1 minus p0 is 1 minus p1, right? So the probability of state 0 is increasing, right? I reduced the number of shots, but when I did it with 100,000 shots, then basically it takes a long time, but then you see much better that when you make parallel measurements, you actually see that it is pretty flat, whereas when you make series measurements, it decays fast. Because every time the state preparation is different in a series measurement. So the state preparation at each point is not the same. Whereas in the orange curve, the state preparation is exactly the same. Were you able to follow that? Any questions? So if you want to measure the decoherence, what we need to do is we cannot use the series one. What we need to do is we need to use the parallel one, because we want to wait after. If we do the series measurements, then that doesn't give you just the decoherence. It gives you both the measurement plus decoherence. So you cannot tell the difference. But if I do the parallel kind of measurement, then I can tell a lot about decoherence. And again, what I encourage you to do is you have the code, so you can change the number of shots and change a lot of parameters and try it out and see what you get. Again, this is only a 10-day course, so we're trying to cover as much as we can, and we're providing you with various resources. And so although we may not be able to go into a lot of details on each topic and each code, what you have is a toolbox. So it's up to you now, right? Whether what you want to do with those tools. So it's sort of a super dense course that is giving you a lot of information and a lot of resources. And I do hope, and we do hope, Dr. Gagi and I hope that you make use of these resources and think about not just understanding quantum mechanics. You have access to a quantum computer, you can actually make measurements, and you can actually do 20, 30 years back, this would have not been possible. Like to measure on a real quantum computer, you would have to be in like some big shots lab and you have to be in a big university or something. But now, just sitting at your home, you can run this on a real quantum computer. So you can think of some experiments that you could do, and you can even think about writing papers. And if there are any good papers that you think will win the Nobel, and we will be happy to help you co-author the paper. And I'm just kidding. But I'm serious about you being able to run more and more experiments or even learn or use it for your courses. But please make use of these resources and try to run the code yourself and try to understand the code and use all the resources. And I hope you get something useful out of it. So we'll stop here because it's already 4:20. And when we come back, I'm going to talk briefly about confusion matrix, and then we will go into modeling this noise through quantum channels, and we'll talk about error mitigation. And I do hope when we come back, we'll come back at 5 o'clock, and that you will have some more questions.